In this lesson, we're going to cover improper integrals. So to start, we're going to consider the infinite region S that is bounded by the curve y equals 1 over x squared, the x-axis, and the vertical line x equals 1. So here's a diagram where we have the graph of 1 over x squared. To the right of the y-axis, it goes like this. We have the line x equals 1, and then we have the shaded region, we're calling it S, that's bounded by the curve and the x-axis and x equals 1. Next, we're going to consider the area of the region described by the following integral. So we have a of t equals the integral from 1 to t of 1 over x squared dx, where again a of t is the area function under this curve from 1 to some value t. So first I just rewrote 1 over x squared as x to the negative 2, and we're going to integrate this. So when we integrate this, we get negative x to the negative 1. And now we're going to evaluate this at t minus evaluate it at positive 1. So since it's x to the negative 1, we want to think of that as 1 over x. We plug in t, so we get negative 1 over t. And then we subtract plugging in 1, but when we plug in 1, it's just 1 over 1, but it's negative. So then negative becomes positive 1. And we can rewrite this as 1 minus 1 over t. I have a note here. It says no matter how large a value chosen for t, a of t is going to be less than 1. So you can see again that a of t equals 1 minus 1 over t. As you pick larger and larger values for t, this fraction gets smaller and smaller, so 1 take away a smaller and smaller fraction is going to be close to 1, but not quite equal to 1. So the area function will always be less than 1. Therefore, when we take the limit as t gets larger and larger of the area function a of t, we can say that it's equal to the limit as t goes to infinity of 1 minus 1 over t, and this limit equals 1. So then, if we take the original integral, and instead we write the integral from 1 to infinity of 1 over x squared dx, it's equal to the limit as t goes to infinity, and then we have the integral from 1 to t of 1 over x squared, and this limit equals 1. So this leads us to the definition of an improper integral. It's a definite integral where the interval is infinite, or f has an infinite discontinuity in the closed interval from a to b. Let's look at this example. It says consider the following integrals. These are considered improper integrals. So this first one is improper because it's an infinite interval. This one's an improper integral because you have the integral from 0 to 1, and then you have this rational function where we have an infinite discontinuity at x equals 1/2. And 1/2 is in the closed interval from 0 to 1. So again, the key is that the infinite discontinuity occurs at 1/2, and 1/2 is in the closed interval from 0 to 1. This integral is considered a proper integral. It also has an infinite discontinuity at 1/2, but 1/2 is not in this closed interval, so it's considered a proper integral. So again, the discontinuity occurs at 1/2, but 1/2 is not in the closed interval from 1 to 2, so therefore it's a proper integral. This definition says an improper integral of type 1. We have part A, if the integral from a to t of f of x dx, where t is greater or equal to a exists, then we have the integral from a to infinity of f of x dx is equal to the limit as t goes to infinity of the integral from a to t of f of x dx. So instead of this infinity right here, we write limit as t goes to infinity and replace that infinity with t right here. For part B, if we have the integral from t to b of f of x dx, where t is less than or equal to b exists, then we have a situation where we have the integral from negative infinity to b of f of x dx, and with this negative infinity, we take the limit as t goes to negative infinity, and we replace the negative infinity with t right here. So then it becomes the integral from t to b of f of x dx. If the limit exists, the integral is convergent. If the limit does not exist, then we say that the integral is divergent. For part C, if both the integral from a to infinity of f of x dx and the integral from negative infinity to a of f of x dx are convergent, then we have the integral from negative infinity to positive infinity of f of x dx, and we can take this and split it up from negative infinity to a plus the integral from a to infinity. Down here's a note, sometimes it is convenient to use a specifically equal to 0. So when you have an integral from negative infinity to positive infinity, again you can break this up, and again it works out nicely using 0. So you go from negative infinity to 0 plus 0 to infinity. This example says determine whether the following integrals are convergent or divergent. So for part A, we have the integral from 1 to infinity of 1 over x squared. This is an improper integral because we have an infinite interval where our upper limit is infinity. So our first step is to rewrite this with the limit as t goes to infinity, and we replace this infinity with t. And then at the same time, I'm going to rewrite this as x to the negative 2. So next we're going to integrate this. So just like the first example in the notes, we're going to plug in t minus plugging in 1. So you end up getting negative 1 over t plus 1. Since t gets larger and larger, this fraction is going to go to 0, and so you just have 1. So right here in the definition of an improper integral type 1, it says if the limit exists, the integral is convergent. So we took the limit and we got the value 1, so it exists. Therefore, this integral is convergent. So I just wrote that out. The limit exists, therefore the integral from 1 to infinity of 1 over x squared dx is convergent. This example says the integral from 1 to infinity of 1 over x dx. So since we have infinity as our upper limit, we're going to rewrite this as the limit as t goes to infinity, and then we have the integral of 1 to t of 1 over x dx. So we're ready to integrate this, and the integral of 1 over x is ln absolute value of x. So now we're going to evaluate this, plug in t minus plugging in 1. So right here we have the natural log of the absolute value of 1. The absolute value of 1 is 1, and natural log of 1 is 0. As t gets larger and larger, this is going to go to infinity. So we just get infinity. And again, according to the definition of an improper integral type 1, if the limit does not exist, we say that the integral is divergent. So I just wrote that out. The limit does not exist. Therefore, the integral from 1 to infinity of 1 over x dx is divergent. So here we have a formula. It says the integral from 1 to infinity of 1 over x to the p dx is convergent if p is greater than 1 and divergent if p is less than or equal to 1. So if you have anything of the form 1 over x to a power, and that power is greater than 1, then this integral is convergent. But if that power is less than or equal to 1, this integral is divergent. This example says determine whether the integral is convergent or divergent. So it's an improper integral because we have our lower limit is negative infinity. So our first step is to bring in a limit in front. Since this has t in it, I'm going to use x in our limit. So we have the limit as x goes to negative infinity, and then I put x right here where our negative infinity was originally. So now we're ready to integrate. Since t is being times by a negative 2, when you integrate, it generates the reciprocal of negative 2, so it's going to generate a negative 1/2. And again, the integral of e to the anything is just itself. If going straight from here to here doesn't make sense, then you can totally use u substitution, where you would let u equal this negative 2t, but then make sure if you're doing that, then you convert your upper and lower limits. So at this point, we're going to plug in negative 1 for t, minus plugging in x for t. Next, we're going to take the limit of the first term plus the limit of the second function. So right here, there's not a variable, so this is a constant. The limit of a constant is just equal to that constant. And here we have an exponential function. So if this was just e to the x, the graph would go like this. It would go up to the right. But since there's a negative in front of the x, that means this graph has y-axis symmetry. So this is what the graph is doing. To the right, it's going down and getting closer and closer to the x-axis. So right here, it says the limit as x goes to negative infinity. So we're looking at this pink graph, and as x is going to negative infinity, that means we're going to the left, and you can see that this graph is going up to infinity. So ultimately, this expression equals positive infinity. So I wrote it out. The limit does not exist, therefore the original integral is divergent. This example is the integral from negative infinity to positive infinity of this rational function. So I just made a note. We have an improper integral. It has an infinite interval, and we're going to use a equals 0 to split this up. So we split it up with the integral from negative infinity to 0 plus the integral from 0 to infinity. Next, I want to look at the function. So we're going to say f of x equals this function x squared over 9 plus x to the 6th. And we're going to check to see whether or not this function is even or odd. So we're going to plug in negative x for x. So again, anywhere you see an x, we're going to substitute in negative x. And since both of these have even powers, they just become x squared and x to the 6th. So this ends up being the same as the original function f of x. And since we get out f of x, that means f is an even function. So since f is an even function, that means we can rewrite this as the integral from 0 to infinity times by 2. So again, integrating from negative infinity to 0 plus 0 to infinity, since f is even, we can rewrite this as 2 times the integral from 0 to infinity of the function. So at this point, in order to evaluate this, we're going to put limit in front and then replace this infinity with t. So we rewrite it as 2 times the limit as t goes to infinity, and it's the integral from 0 to t of the function. So now at this point, we need to integrate this. So in order to integrate this, first I'm going to rewrite the denominator. So I'm going to move this x to the 6th in the front, and I'm also at the same time going to rewrite it as x cubed quantity squared. Next, we're going to move the 9 right here, and we're going to rewrite it as 3 squared. So now, in order to integrate, if you look at the denominator, you have something squared plus a constant squared. So ultimately, we want to use the tan inverse formula in order to integrate this. But first, we're going to let u equal this x cubed. So now we're going to take the derivative. So we get du dx equals 3x squared. And then we'll rewrite this. So we get du over 3x squared. And finally, we're going to convert our upper and lower limits. So first, we take the t and we plug it in right here for x. Then we take the 0 and plug it in for x. And finally, we're ready to plug everything in up here. Okay, so at this point, you can see that these x squareds are going to cancel out. Next, I'm going to pull this 3 to the front, making it a 2/3. And now we're ready to integrate. So this is in the formula of x squared plus a squared. And again, if this was written as x squared plus a squared, the formula is 1 over a tan inverse x over a. So to integrate this, it's going to be 1 over 3 tan inverse u over 3. And then remember, because we converted our upper and lower limits, we don't plug u back in. We just take the converted limits and we plug in t cubed minus plugging in 0. And I'm also going to bring this 1/3 to the front, making it 2/9. So now we have this expression. So I drew the tan inverse graph over here. It hits 0, 0, and then to the right, it approaches a height of pi over 2. To the left, it approaches a height of negative pi over 2. So when this says the limit as t goes to infinity of tan inverse of an expression, as t gets larger and larger, the tan inverse graph is going to approach a height of pi over 2. So this part of the problem is going to go to pi over 2. And then tan inverse of 0 is just 0. And so the limit as t gets larger and larger of this expression is just going to be pi over 2. So we end up getting pi over 9. And I wrote it out. The limit exists, therefore this integral is convergent. Our next definition is an improper integral of type 2. Part A says if f is continuous on a to b, where a is closed and b is open, and discontinuous at b, then we have the integral from a to b of f of x dx equals the limit as t goes to b from the left of the integral from a to t f of x dx. So again, if f is discontinuous at b and b is the upper limit, you're talking about the interval from a to b. So we replace b with t, and then we write limit as t goes to b from the left. And again, it's b from the left because your interval is going from a to b. And so if you're going from a to b, we're approaching b from the left. Next, if f is continuous on the interval from a to b, where a is open and b is closed, there's a discontinuity at a, then again, a is a lower limit this time, so we say the limit as t approaches a from the right, and then we replace the a with t, and then we do the integral from t to b of f of x dx. Finally, if f is discontinuous at c, and c is in between a and b, and we know that both of these are convergent, then we can write the integral from a to b of f of x dx is equal to the integral from a to c plus the integral from c to b. This example says to evaluate the integral from 1 to 9, and it's 1 over the cube root of x minus 9 dx. So when looking at this function, you can see that we can't plug in 9 for x, and 9 is the upper limit. So I wrote this out. This is an improper integral. It has an infinite discontinuity at x equals 9. Therefore, f is going to be continuous on the interval from 1 inclusive to 9 not inclusive. So we're going to replace this 9 with t, and we're going to bring a limit in front. So again, we're talking about the integral from 1 to 9, and again, 9 is the value that causes the issue here. So we replace the 9 with t, and we say the limit as t approaches 9 from the left, because again, you're going from 1 to 9, and you're approaching 9 from the left. Next, to evaluate this integral, we're going to use u substitution, and we're going to let u equal this x minus 9. So we're going to take the derivative, and then we're also going to convert our upper and lower limits. So we're going to take this t and plug it in right here for x, and we're going to plug in 1 for x as well. All right, and we're ready to plug all of this in over here. And then one last thing before we integrate this, I'm going to rewrite this as u to the negative 1/3. And now we're ready to integrate. So now we're going to plug in our upper limit minus plugging in our lower limit. And I'm also going to bring this 3/2 to the front. So now we're going to take the limit of this first expression minus the limit of the second expression. As t approaches 9 from the left, this expression is going to go to 0. And then right here, we're going to take the cube root of negative 8, which is negative 2, and then square it and get 4. And the limit of 4 is just 4, so here we have 3/2 times negative 4. So we end up getting negative 6. So the limit exists, therefore the integral is convergent. For this example, we're going to evaluate the definite integral from 0 to 2, and we have this rational function. This is an improper integral because if you look at the denominator and you set it equal to 0, you get 3/2. And 3/2 or 1.5 is in the closed interval from 0 to 2. So what we're going to do is, since this is discontinuous at a value in between 0 and 2, we're going to break this integral up. So when breaking it up, we take the integral from 0 to 3/2 of the rational function plus the integral from 3/2 to 2 of the rational function. So now these are improper integrals of type 2. So if we look at this one right here, It follows this definition for part A. This function is discontinuous at b, so instead of b, we replace it with a t, and we say the limit as t approaches b from the left. And again, I wrote this over here, evaluate one limit at a time. If one diverges, the entire expression diverges. So let's just work on this one for now and see what happens. So now we need to evaluate this integral. Since the degree of the numerator is equal to the degree of the denominator, we're going to use long division. So we're going to say what times 2x makes x? So that's going to be a 1/2. Then we multiply this to both of these terms and write it down here. And then we add their opposites. So we rewrite this rational function as 1/2, so right here, plus, and then this is the remainder, so -3/2 over the thing we divided by, 2x minus 3. And next we'll take this integral and we're going to split it up. So we'll do the integral of 1/2, and then we'll do the integral of this expression. So again, right here we have the integral from 0 to t of 1/2 dx. And then for this guy, I moved the -3/2 to the front. We have the integral from 0 to t of 1 over 2x minus 3. So we can integrate this right away, but over here we're going to use substitution. And we'll let u equal this denominator, 2x minus 3. So right here I'm going to integrate. With respect to x, the integral is going to be 1/2 x. And then we'll plug all of this in right here to evaluate this integral. So on this side, we're going to plug in t minus plugging in 0. I got everything plugged in, and I'm going to move this 2 to the front, making it a -3/4. And then we'll integrate 1 over u, which is ln absolute value of u. And finally, we'll plug in 2t minus 3 for u, minus plugging in -3. I got those plugged in, I dropped down the 1/2 t, and next, the absolute value of -3 is just 3. So here we have minus ln of 3, and then we'll distribute this -3/4. And finally, it's the limit as t approaches 3/2 from the left. So for this first expression, that would just be 1/2 times 3/2, or 3/4. This last expression is a constant, so the limit of a constant is just the constant. So finally, we want to look at this right here as t approaches 3/2 from the left. So I put this expression in the graphing calculator, and you can see that we have a vertical asymptote right here at 3/2. So when we're approaching 3/2 from the left, the curve goes up to infinity. So this entire expression is going to go to infinity. So since we got infinity for this first limit on the left, the limit does not exist. Therefore, this part of the problem diverges. And since one of them diverges, the entire expression diverges. So we can conclude that the original integral from 0 to 2 of the rational function is divergent. All right, guys, thanks so much for watching.